the heading on your sheet is geometry of the derivative. Another way you could call it is it's a visual approach to differentiating, but also to actually going the other way, which hasn't got a name yet. You could call it anti-differentiation, but we'll deal with that a lot later on. What's the idea? This is like actually differentiating without all the work, okay? This is what a function looks like, okay? So you might notice the axes are all labeled a bit differently. Up the top you've got y, okay? I've been a little bit naughty for the sake of brevity. I've called the next one y dash, and the next one with that y double dash. Okay, so first and second derivatives. So the idea is, what we want to do is, even though we don't know any numerical values here, okay, we can read off the features of this graph and it will tell us about each of the derivatives. And also, as you'll see later on, it goes the other way too. Okay? So, with your other colour, what I want you to do is first, let's take note of all of the critical points that we know about. Critical points, okay? Now, I can see 3 on this graph. Can you tell me what they are?
There, and there.
There, and there. What an unhelpful...
There, 1, and there, 2.
Can you tell me what they are?
2 turning and 1 the deflection.
Okay, good. So I've got a max turning point here. Okay. I've got a minimum turning point here.
Yeah, you were right.
And in between the turning points, I have a point of inflection. Okay. Now, points of inflection, they're a bit tricky. So what I would recommend is you get your ruler out, okay, and you stick it over on the left-hand side, and you move it across. Now, what you want to look for is the point at which it's no longer all concave one way or the other. Okay. So, for instance, let me just put this lid back on. For instance, you can see if I put the ruler here, that's pretty obvious. Everything to the left is concave down. And I can keep doing that for a little while. And then if I've gone here, you can say, oh, I've gone too far. Okay? So there must be some point in here that I can say, well, it looks kind of like it has no concavity. So an easy way, just generally, most graphs, it depends on the ones you've got, most points of inflection tend to be about halfway between turning points. Okay, have you noticed that? It's a sort of a pattern. Not always, but often. Okay? So I'm going to put it somewhere around here. Okay? So now, again, take your ruler. We'll do the first derivative first, because it's the first derivative. Stationary points, right? What do stationary points tell us about the first derivative?
0.
It should be 0, right? So take your ruler and rule down from your turning points, from your stationary points, down to your first derivative graph. Okay, like so. Okay, you actually could, but I'm going to leave it for now. I think this is sufficient, okay? Because what I want to say now is, alright, at these 2 points, I should have stationary points, so I should have the first derivative being 0. So these two will be intercepts, right, for the first derivative. Now, what happens after that? I want to come back to my top graph, okay, and I want to notice what its shape tells me about the sign of the first derivative. Do you remember us thinking about this? So, to the left of the turning point, what's the gradient like? Well, it's positive, right? Because the graph is increasing. Positive, 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 positive. And then 0. Okay? In between the turning points, the gradient is negative. Negative, 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 negative. Okay? And then it resumes being increasing. So, positive, 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 positive. So if you like, what this is equivalent to is shading regions for down here, okay? Because to the left of this root, I should be above the axis. It should be positive. In between, it should be negative. Right? I should be below the axis. Now, one more quick question. Where are you going to expect the derivative to be lowest? Where should the derivative be lowest? It would correspond to the point of inflection, right? Because that's where it's steepest, right? You know, here you're not very steep at all because it's next to the stationary point. Here you're getting steeper and steeper until this point, and then you stop getting steeper and you start getting shallower again, right? So therefore, this point here should correspond to the lowest point of our first derivative. Okay, so this is what I'm going to have. Okay? And in fact, you should be able to take your ruler and draw down from that point of inflection, which should line up with this vertex, okay, which I'm going to do now. Okay? Welcome back. Have a seat. Alright, I'm almost done. Sorry? Okay, so a couple of things. Let's say on this graph here, okay, stationary points correspond to roots for the first derivative. Okay?
It's made for cubics, right? The point inflection is always right in between the max and min points.
Well,
Otherwise, the parabola.
what does that imply? Because for a quadratic, right, the vertex will always be halfway between the roots, right? So exactly right. Yes. So if you didn't catch that, right, when you have a cubic, your point of inflection is always exactly halfway between your turning points. But as you increase powers, like say x to the 4, you're still going to have turning points, but the points of inflection will be off to the side. They'll be skewed. Okay? Does that make sense?
Yeah.
Okay, last one. Let's do the second derivative, which is very quick. Because this is like something cubed, this is like something squared, so this is going to be a straight line, right? Now this point of inflection corresponds to a root for the second derivative, okay? So I'm going to pass through there. And you can also see, have a look here, right? This is concave down, this part of the graph, and this part is concave up. So concave down means a negative second derivative, and concave up means a positive second derivative, right? So this is the kind of second derivative I'm expecting, okay? Ta-da, finished. So that wasn't too bad, was it? By the way, you'll notice, like, I don't know any of the distances here or anything like that, or scales. So this parabola could just as easily have been this parabola. Okay? It still has the same stationary point, it still has the same vertex, and in the same way this could be, really flat. It's still obeying the same laws, okay?